the role of randomness. Well, I don't know what you mean by the role of randomness. You see, first of all, what is randomness? There is an eternal problem about what you mean by something being random. You see, you can have, for example, you can have a random number generator, okay? That's well known that that produces numbers that look random, as they say, but which is produced by a perfectly deterministic mechanism. And we have lots of mathematical, I mean, not even practical things like the random number generator, which is in the end periodic probably, but you can make mathematical models of dynamical system, perfectly deterministic dynamical system, whose behavior is completely random in certain ways. That's very well known. It's known as chaos theory or the modern theory of dynamical systems. So it's very hard to see what, you see, it's something which was explained by Laplace in his essay on probability. I mean, he says things, we call things random when they occur without regularity, and we call them non-random when they occur with regularity, like the motion of the moon or the planets or maybe the comet and so on. But where is the intrinsic difference? Well, the difference appears to be only due to our ignorance. We know certain things, we don't know others, we can compute certain things, etc. Of course, the fact that we cannot compute certain things is related to the complexity of the dynamical system. If the system was very simple, we could compute it, therefore it would look random. But that still remains not, it's very difficult to make a sharp distinction between a system which would be, you know, well, you can make a mathematical definition of what in practice would be predictable and not predictable, but I think most systems in the long run would be unpredictable. And so you have to distinguish between determinism and predictability. So things can be perfectly deterministic and unpredictable. And if you define randomness by non-deterministic, then it's very difficult to give a criteria that tells you that something is random. And quantum mechanics is a good example because there things look random, but Brownian mechanics being deterministic, of course, says that you can account for those things on the basis of deterministic laws. Of course, you have to assume initial conditions that are, in some sense, random, but of course, what does it mean? I mean, they are determined initial condition, and given those initial conditions, the world will look the way it looks, namely random. But it's important to realize, I mean, I don't think that, for example, on a Brownian theory point of view, there is not much difference between the randomness in statistical mechanics and the randomness in Brownian mechanics. I mean, they're just certain initial a class of initial conditions will make the world look the way it looks in both cases, and you have a deterministic dynamics between the two. So you have an initial condition of the system, deterministic dynamics, and then the end result. And the end result looks whatever it is, given the assumption on initial condition. And that's what you can call random if you want, but there's nothing intrinsically random about it. So I wouldn't say that, I wouldn't even say that on the Brownian account, things are very different in quantum mechanics than in classical physics, from the point of view of randomness. Okay, to understand Bell's inequality, you have to understand an article by Einstein, Podolsky, and Rosen, which is almost 30 years before, so that was in 1935, and Bell came with his inequality in 1964. And what Einstein, Podolsky, and Rosen notice is that there are certain systems, so that when you do certain measurements on those systems, I mean, there are certain systems made of two particles, let's say, that are sent and they can be as far away as they want. And if you do one measurement on one of them, then if you do the same sort of measurement on the other, you will always get perfectly anti-correlated results. So which means that if the answer is going to be plus, because these are measurements that can take two values, plus and minus, let's say, then if it's plus on one side, then it's necessarily going to be minus on the other. And that's true for all sets of measurements that you can do, but provided you do the same measurement on both sides. So you find these perfect correlations. And Einstein, Podolsky, Rosen said, look, if you assume that the measurement here, so do a measurement here and don't do a measurement there, and let's forget about relativity. Let's say we do it, we have a universal time. Let's think in those ways. So you have one measurement here, and you don't do a measurement there. So when you do the measurement here, you get one result, let's say plus. Then you know that any measurement there of the same thing will give you minus, whether you do it or not. So they say quantum mechanics is ambiguous about what it means. Quantum mechanics seems to say that there is no fact of the matter as to whether it's plus or minus before you measure, because everything is produced by measurement. But then Einstein, Podolsky-Rosen said, look, if you measure here and you get a definite result, then you also get a definite result there. So before there was no fact of the matter as whether it was plus or minus over there, and now there is a fact of the matter as to whether it's there, plus or minus, without me doing anything over there, but doing something here. Okay? So I do something here, and I change a non-fact of the matter into a fact of the matter over there. So I change the physical situation over there, because before it was indeterminate, now it's determinate. And then Einstein, Podolsky-Rosen said, obviously, that can't be so. I mean, you can't act at a distance and change the physical situation over there by doing a measurement here and doing nothing over there. Therefore, and that's the logic of the argument, therefore, it must be the case that the result was already predetermined there, over there, before I do the measurement. Well, I don't do a measurement there, but before I do the measurement here, it was determined there. And that's the substance of their argument. The way I state it was reformulated by Bohm later, but basically that's the substance of their argument. Now, there is something wrong with their argument, but there is something which is absolutely correct. If you reformulate it, I will get to what is wrong, but if you reformulate it in the following way, either things were predetermined, or by acting here, I can influence the situation there, either or. If you do it like that, then that seems to be obvious to me. One of the two must be true. There is another example which I gave in my talk, which is even easier to understand. You take a box with one particle in the box, cut the box in half, send the boxes, one to Tokyo and the other to New York. Then according to quantum mechanics, the particle is half in one box and half in the other. But what does it mean? Suppose you open one of the boxes and you don't find the particle. Then, of course, you are sure that it's in the other box, and if you open the other box, you will find the particle. Now, what does quantum mechanics say about it? You see, you could say the following dilemma. Either the particle was, there is a matter of fact that the particle was in the box before you open the one where you don't find it. It's in the other box. But then, of course, that's exactly what Einstein, Podolsky-Rosen wanted to say. Quantum mechanics is not a complete description. There are facts of the matter which are not incorporated in quantum mechanics, in the quantum description, which is sort of, vague about that. There are facts of the matter. Or, by opening the box here and not finding the particle, you somehow condense or change the state over there, and that's sort of an action at a distance. And so, again, the dilemma seems to be unavoidable to me. It's either or. But then, of course, you could say, well, the action at a distance being unreasonable, it must be that there's a particle there. And that's basically what Einstein, Podolsky-Rosen said. So I think they're reasoning, saying that either or, either P or Q, where P means some action at a distance, and Q, or some influence at a distance, and Q means there were already predetermined values, seems to be unavoidable, the dilemma. What is not correct is they say action at a distance is absurd, therefore there are these predetermined values. Because what Bell showed is that if you look at measurements along when you don't do the same measurement on both sides, then you get statistics that cannot be reconciled no matter what you do, and that's a simple mathematical fact, can't be reconciled no matter what you do, with the idea that the values are predetermined. And that's the strange thing, because you see, Einstein, Podolsky-Rosen were making a valid argument and making a very sensible extension of that argument. The valid argument is still there, it's either or, but what is not valid is their sensible conclusion, because it's the unsensible of the two, of the P and Q, P being non-locality is unreasonable but true, and Q being the fact that those values pre-exist is reasonable but false, okay? And so what is being clarified over the years, and clarified mostly by Bell, is actually, Bell showed that actually the sensible conclusion does not work. So there is a sort of non-locality in the world. But of course it's a subtle sort of non-locality, because naively you would think that non-locality means by waving my arm I can sort of communicate directly with Munich or with the other side of the galaxy and so on. And that, of course, I can't do. So I can't communicate, send messages and so on. So the sort of, that's too long to explain for the interview, but that's a well-known fact. And of course, that sometimes taken by people to mean that actually there is no non-locality. And in a strong sense of the word, in the sense that sending messages, there is no non-locality. But there is a subtle form of non-locality, which is often missed by people, which is basically the fact that, you know, certain facts over there influence the statistics, at least, of the result over there. Certain facts over here may influence at least the statistics of the result over there. And in a way which cannot be accounted for by saying they come from a common source. Naively, you would say, well, these things come from a common source, so they have some sort of instruction that tell them how they're going to behave, and the instructions are correlated. That would be a local way to explain the correlation, and that's verboten by Bell's results. So Bell's tells us something, one of the most extraordinary, I think is the most extraordinary result in the whole history of physics, the weirdest thing we have learned about physics. You see that there is this subtle non-correlation between us and everything else in the universe in some sense, you see. What to make of that? Well, luckily Bohm's theory accounts for that, so that's, Bohm's theory is perfect because it explains both why you can't send signals, you can't send messages, but nevertheless you have this non-locality inside the theory. So then, of course, people don't like Bohm, want to have their cake and eat it. They say, well, Bohm is non-local, but then they say Bell has refuted the hidden variable theorem, which isn't true. Bell has shown that the world is not, you have to assume realism and so on and so forth. You don't have to assume anything. EPR shows you that you have this correlation, and this correlation have to be accounted either by being there before you measure or because one measurement influences the other. There is no other way. And then it's the latter one which is true. That's what Bell shows. So it does show that there are these influences which are non-local. You can't think of the world. You would like thinking of the world of, Newton, of course, had action at a distance. In Newton's theory, by moving your arm, you influence the motion of everybody in the universe instantaneously, but of course in a way which can't be detected. But in principle, because Newtonian mechanics depends, every gravitational attraction between parts of the world is related to the mass distribution and so on. If you change the mass distribution, then of course you change the, you change the motion of everybody, all the bodies in the universe in principle. But that's not the, that's something which people wanted to get rid of. When people introduced electromagnetism, general relativity and so on, they wanted to move away from this idea of instantaneous connection. And now we have not only a theory that gives us that, but also a proof that every possible theory will have that in a very subtle way. And so that's exactly what is bothering, what is surprising in the result of Bell's inequality. But of course, it's only surprising if you combine Bell with EPR. If you just take Bell, then it doesn't tell you anything very surprising. It's only when you combine with EPR that you arrive at the right conclusion, which is surprising, which is this lack of locality of the world. And that's what to do with it. Well, that's it. We have to live with it.